theorem.
Thank you. Yes, so let's quickly recall Herbrand theorem. For this, we need the notion of universal theory. As you know, is a theory whose axioms are all universal closures of quantifier-free formulas. Just to have an example, the theory of partial orders, flexibility, transitivity, and symmetry are all universal statements. Or also the theory of partial orders with min and max, if you take these as constants. For example, for all x, min is less or equal than x. Okay, in Herbrand's theorem, let's say in a very simple case for existential statements with one free variable, it says that if T is a universal theory in a language which has at least a constant symbol, and I have a formula alpha x, quantifier free, then the theory proves exist x alpha x if and only if there are term-definable constants, so ground terms C1, Cn, finitely many, such that T proves the disjunction of alpha of Ci with us I between 1 and n. Okay, just as an example, in the theory of partial orders with min and max, the sentence exists x max less or equal than x is provable by T because T proves that max is less or equal than max. So we have replaced this ground term into x. Okay, this is actually the easy direction. And the other one is, in this case, if you consider the sentence exists x strictly between min and max, the theory T does not prove it because, applying Herbrand's theorem, T does not prove any of the two instances where we replace x by the only term definable constants we have, min and max, as well as T does not prove any disjunction made up with them. All right, and okay, just as a side note, these hypotheses that the language has at least a constant symbol, this formulation is needed because otherwise, for example, this can be proved exists x equals to x, but we might not have enough weakness in constants. However, it can be removed, this hypothesis, if we either replace constants by terms, so that we can use variables, or we use a version of classical first-order logic, whose semantics admits empty structures. Okay, this is just a side note. Okay, now I was interested in an algebraic version for this theorem. I'll say a bit about my motivation later. But what does algebraic mean? Well, it means that we have to consider the algebras of the logic. In this case, these are first-order Boolean doctrines. And these are to classical first-order logic, just like Boolean algebras are to classical propositional logic. So just to sketch a definition, fix a functional language f, and roughly speaking, a first-order Boolean doctrine is what you get if you take a set of relation symbols and a theory T in the language made up of f and r. You consider all formulas in this language, and you mod out modulo T interprovability. Okay. Also, as a warning, maybe some of you is familiar with the definition of first-order Boolean doctrines as certain functors from the opposite of a category to the category of Boolean algebras, where C takes the place of F, but in this talk we avoid this categorical phrasing. Okay, and what is a first-order Boolean doctrine of a functional language F? So these are algebras of classical first-order logic. Well, they consist of a family of Boolean algebras. Okay, here we don't take just one Boolean algebra, but we index, we take one Boolean algebra for every finite set of variable. And that Boolean algebra is the Boolean algebra of formulas with three variables drawn from the defined set. And we need these many families so that the quantifiers behave better because they change the set of three variables. Then we have, as part of our algebraic structure, substitutions. So whenever I have two finite sets of variables and a function from the first set to terms in the second set, then we have a Boolean homomorphism from P of x, which you should think of as the Boolean algebra of formulas with three variables in x to P of y. And this is essentially the substitution where to each variable x we replace sigma of x, which is a term with three variables in y. And then as the last item of this algebraic structure, we have quantifiers. Quantifiers go from P of x union variable y to P of x. And essentially, you should think of them as a function that take a formula alpha and map it to exists y alpha. And here we remove the variable y because it's no longer free. And certain actions have to be satisfied. So these are factoriality of substitutions, the fact that quantifiers are adjoined to adding dummy variables, which is called the Beck-Chevalier condition, and that quantifiers commute with substitutions provided a certain side condition. And if you want the equality, you can add it, but let's not take it for simplicity. Okay, and first order Boolean doctrines are the algebras of classical first order logic. And here, as a disclaimer, here we mean the logic in which we allow, whose semantics allow the usage of empty structure. But if you don't want empty structures, then you can restrict to the Boolean first order Boolean doctrines which satisfy that exist x is stop. Okay, to phrase Herbrand's theorem in this setting, this algebraic setting, if you recall, we start with a universal theory. A universal theory here corresponds to Boolean doctrines. A Boolean doctrine is the same as the first order Boolean doctrine, but without quantifiers. So it's a family of Boolean algebras. We have substitutions, which are Boolean homomorphisms satisfying factoriality as a family, but we don't have quantifiers. Essentially, this is because universal sentences, you can think of them as a quantifier-free theory. A quantifier-free theory that might have free variables. Okay. Right. So if Boolean doctrines don't have free variables, we might need to freely add free variables. And here comes a nice thing about first order Boolean doctrines, which is that they are defined, they can be thought as many sorted algebras in the standard algebraic sense, and they are definable by equations. So they form what is called a variety of algebras, and this means that this implies that all free algebras exist. We can do free constructions. Okay, in these settings, it means that the forgetful factor from the category of first order Boolean doctrines over f to the category of Boolean doctrines over f. So we don't have quantifiers anymore in Boolean doctrines. This has a left adjoint. There's a way to freely add quantifiers, and so here this means that we have a Boolean doctrine P. There's a first order Boolean doctrine P for all exists called the quantifier completion, in which the quantifiers are freely added. and we have some comparison. So just like the set of quantifier free formulas embeds into the set of first order formulas, this px embeds into the value of the quantifier completion at x. Okay, let's see Herbrand's theorem in this algebraic form. Okay, so instead of having a universal theory, we have a Boolean doctrine over functional signature. So just think of this Boolean doctrine as the quantifier-free part of the set of formulas modulo the universal theory T. And now, given alpha in P of x, so a formula with a free variable x, then, well, what does it mean that T proves exists x alpha x? Now, we cannot talk anymore about exist x alpha in P, because P does not have quantifiers, but we can talk about exist x alpha in this quantifier completion. And here, exist x alpha is true if and only if there are term definable constants, C1, Cn in this signature, such that, well, already in P, this substitution, the join of these substitutions is true. Okay, so just two small remarks. We don't need existence of constants in F, essentially because the logic of first order Boolean doctrines is does not exclude the empty set in their semantics. And moreover, here T cannot be a general arbitrary theory, and this corresponds to the fact that here this first order Boolean doctrine cannot be just any first order Boolean doctrine extending P, but it has to be the free one. Okay. And actually, okay, our initial motivation was to, starting with P, understand how this free algebra is made, and then we realized the connection with Herbrand's theorem. Okay, and we wanted to do this because of the importance of free algebras in the study of algebras related to logic. Okay, and okay, although I phrased it in a certain way in this talk, actually we proved it in the setting of first order Boolean doctrines defined as certain functors from the opposite of a category. We find products to the category of Boolean algebras, and this is a nice way to also prove the same for many sort of classical first order logic without too much denotational complications. And I cannot sketch the proof now, but the proof uses models. And to produce them, we use a proof similar to Henke's proof of Gödel's completeness theorem. And we combine this technique of using models with the universal property of the quantifier completion to get the result. Okay, more details are in this preprint. Thank you.